Now, as the Big Bang occurred, we started out with those tiny, tiny bits of time called Planck time, 10 to the negative 43 seconds, and we don't know if it's physically possible for us to ever know what occurred prior to that time. Through that, there are these eras that we'll talk about a little in a next video or a future video here. Then there were these eras where particles started to occur, and by the time we got to 1 to 3 minutes, the temperature had cooled enough to about 10 to the 10th Kelvin that particles slowed enough to actually create protons and neutrons out of those quarks. This is called, in the history of the universe, the era of nucleosynthesis. Synthesis means to make. Nucleo, of course, means nucleus. So by the time there was 1 to 3 seconds in the universe, we had the particles that would eventually become the nuclei of our atoms. Now, atoms had not been created yet. The universe hadn't cooled enough for electrons to come into being part of atoms, but the nuclei were produced. By the time we got to time as 3 minutes to 20 minutes, the universe had cooled down to about 1 billion degrees Kelvin, and the first atoms formed. Now, this is going to be about 75% hydrogen and 25% helium. That's what was predicted by the Big Bang Theory, and that's what we're observing when we look back at that early universe. And this is a huge piece of evidence that the Big Bang Theory is on the right track. We're looking at things the right way because observation is matching the theory. So there are 4 pillars of cosmology, and the 4 pillars of cosmology are the pillars of what makes Big Bang Theory not just somebody's wild guess of what they think may have happened, not just a cute creation story created by someone trying to explain that babies come from under cabbage leaves. This is based on an awful lot of experimentation and evidence. And the 4 major pillars of Big Bang Theory are: 1, the universe is expanding. Well, we can see that because of the Hubble constant and that expansion and Doppler redshift. Big Bang Theory predicts that about 75% of the early universe will be hydrogen and about 25% will be helium, and that's what we observed when we look back to the light that is as old as our universe. Big Bang Theory predicts there should be a cosmic microwave background radiation that when the universe was produced had a peak blackbody curve of around 3000 Kelvin, and because of the Doppler shift and that expansion of the universe from very small to very big, that has spread. So now that background radiation is right around 3 Kelvin, and we've observed that. And we can observe the evolution of the universe over the last 13.8 billion years. We have observed situations where there were primordial galaxies and then more advanced galaxies and hydrogen and helium, and now to the day in our galaxy where we have all of the various elements on the periodic table. These pillars of cosmology are the big pieces of evidence of why Big Bang Theory is actually correct. Now, by the time we got to time is about 3 minutes after to about 380,000 years, the universe is full of hot plasma, nuclei of hydrogen and helium, and a soup of electrons. Kind of picture it as a hot soup. All of this stuff is swirling around, incredibly hot. And it is so hot that the electrons cannot bind themselves to protons and neutrons to actually form atoms. At about 380,000 years, sorry, I want to say that right, after the Big Bang, the universe all of a sudden becomes visible. And when it becomes visible, then atoms combine, light can be produced, and we can see to that point. We can't see beyond this point, but we can see to that point. From about 380,000 years to 150 million years after the Big Bang, there was an area that is called Dark Ages. And it's called the Dark Ages because the universe is dark. There's no real light to see. We can see the glow of the Big Bang. We can see the microwave background radiation, but we're not seeing stars. There are basically no stars. This is the time when gravity is dominating and gravity is pulling everything together to create stars so that we can get to first light. Now, we're still trying to understand dark matter. And as our understanding of dark matter gets better, we will have a better understanding of what was going on during this period of galactic history. From about 150 million years to about 1 billion years, this is called the era of reionization. Reionization means when we got these cold little hydrogen and helium atoms into a position where they're actually inside of stars, and they got hot enough that we could have light produced. So the universe is still expanding very rapidly at this point in history. There are slight variations in the density of matter from one part of the universe to another, and gravity itself is causing clouds of gas to collapse very, very rapidly to produce the first stars, the first galaxies, the first black holes, and of course, quasars. During this reionization era, the first stars were produced. This is this era of first light. The first stars were very hot. They were giant stars, lots and lots of hydrogen. None of the other elements, aside from helium, had even been produced yet. These were big stars that were very blue, very hot. They lived fast and they died hard. They did not stick around for a long time, but their life cycle created all of the other elements that go into making you and I. So we're talking today about, like, there's the Big Bang and this era of when the universe became visible, it stopped being opaque. Then there's this Dark Ages, the era where there were no stars. Then we have an era where enough gravity produces stars and the early galaxy. And again, creation of the universe, this point in history where the universe stops being opaque, the Dark Ages, no stars, and then the first light, when the first stars started being produced somewhere around 400 million years after the Big Bang. Now, I've gone through an awful lot of detail very quickly, and I'm going to ask you to watch some of the big, important, beautiful videos that are out there to help explain this. Maybe